Welcome to my video lecture on equivalent circuit of single phase induction motor. In my previous lecture, we have discussed about double revolving field theory and cross field theory, and we also discussed about why the single phase induction motor is unable to start or is not self-starting. And that phenomenon we have already explained by using double revolving field theory and cross field theory. Now in this lecture, we will show the equivalent circuit of single-phase induction motor. We know that equivalent circuit is based on the equivalence of a circuit or a device or electrical machine, and that in that equivalence we will definitely maintain the principle or phenomenon of that machine itself. So here we will develop the equivalent circuit based on double revolving field theory itself. So when we are talking about the double revolving field theory, and there we have learned how that double revolving field theory established the concept of single phase induction motor, and from there we will develop the single phase induction motor equivalent circuit. So in equivalent circuit, the most single phase motors are in fact two-phase motors. Why it is called two-phase, that part we have already discussed in our last lecture, in which an auxiliary winding is disconnected from supply when the machine reaches a certain value. I have already discussed in my previous lectures that when the machine will reach 70% of its rated value of speed, then the auxiliary winding is automatically disconnected from that machine by using centrifugal switch or relay. The machine then operates a truly single phase motor, but before that it acts as the two phase motor. We shall develop a equivalent circuit of single phase induction motor running only on main winding M. First, consider the case when the rotor is stationary and only the main winding is excited. So first we will considering that only main winding is excited and our rotor is stationary at that case. Okay. The motor will behave like a single phase transformer. At that case, the motor will behave like a single phase transformer. Remember this one. The motor will behave like a single phase transformer with its secondary short circuited. So the equivalent circuit is stationary rotor that we will show in our next slide, and here the core loss branch we will not show, and the core loss will be assumed that to be lumped with the mechanical and stray losses as part of the rotational losses of the motor. So definitely the equivalent circuit of single phase induction motor will be also similar like equivalent circuit of single phase transformer. So here this is the equivalent circuit of single phase transformer when only main winding is energized and the motor is at standstill, because we know that only by energizing main winding the motor will unable to start because it's not self-starting. We need the auxiliary winding for start the motor. So here R1M is the resistance of the main winding, this one. Then XYM leakage reactance of main stator winding. XM magnetizing reactance, this one. Then R2 dash is the standstill rotor resistance referred to the main winding of stator winding. Then X2 dash is the standstill rotor leakage reactance, again referred to stator main winding. Then Vm is the supply voltage and Im is the main current. This is main current and this is the supply voltage. And in this case, we are assuming that the loss component branch is neglected because all the losses are considered here as rotational losses. Okay. Now, according to double revolving field theory, the pulsating air gap flux in a motor at standstill can be resolved into two equal and opposite fluxes with the motor. Since the magnitude of each flux is rotating flux, each one half of alternating flux, it is convenient to assume that the two rotating flux are acting on two separate rotors. According to double revolving field theory, which we have already discussed in my previous lecture, that single phase induction motor are considered as consisting of two motors having stator winding of two imaginary rotors which rotate in opposite direction. That is based on our double revolving field theory, and we are imagining that two opposite fields are rotating because our supply is sinusoidal in nature, and for first half it is rotating in one direction and for second half it is rotating in another direction. So the standstill impedance at each rotor referred to the main winding is R2 dash by 2 plus jx2 dash by 2, which we have already taken in previous diagram, that is it is R2 and x2. Now we are dividing this R2 dash into two equal half and x2 dash into two equal half. So it becomes R2 dash by 2 and x2 dash by 2. So our rotor is now divided into two parts, one for forward field and another for backward field. So our rotor becomes divided into two portions. The equivalent circuit of single phase winding of induction motor with stationary rotor is shown in figure 8.6 here, this one. And this diagram, the portion of equivalent circuit represents the effects of air gap flux is splitting into two portions that I have already shown you. The first portion shows the effect of forward rotating field flux, and second portion showing the effect of backward rotating flux. That means the total equivalent circuit is now divided for forward field flux and backward field flux, and the remaining part is same. The stator main fielding portion is same, and only the rotor part we have changed according to the double revolving field theory. The forward flux induces a voltage EMF in the main stator winding. Okay, that we have already shown you. This is the main field flux EMF is EM. This is the main EMF which is generated. Now we have divided this EMF and EMB according to backward field and forward field. That means the total EMF is generated by combination of forward field and backward field. So the resultant induced voltage in the main stator winding EM is basically EM equals to EMF plus EMB. The circuit of forward and backward rotors are identical under standstill conditions, as the rotor has same slip with respect to each rotating flux. Thus, EMF and EMB are equal. Now, suppose the motor is started with the help of auxiliary winding. It is further assumed that the auxiliary winding is switched out. After that, the motor gains its normal speed. The effective rotor resistance of induction motor depends on the slip of the rotor. The slip of the rotor with respect to forward rotating flux is S. Thus, the effective rotor resistance in the portion of the circuit associated with forward rotating flux, it becomes R2 dash by 2S, because the forward rotating flux slip is S. Now, the slip of the rotor with respect to the backward rotating flux, that is 2 minus S. We know that the slip which is generated due to backward field, that is 2 minus S. Therefore, the effective rotor resistance referred to stator in the portion of the circuit associated with backward flux, it becomes R2 dash by 2 into 2 minus S. Now our equivalent circuit with respect to slip, it will again modify the rotor part, and that will be becomes like this. This portion we have added slip. This is for forward field and this one for backward field indeed. When the forward and backward slips are taken into account, the result of the equivalent circuit is represented here, 8.6C. Okay. The rotor impedance representing the effect of forward field referred to the rotor stator winding M is given by R2 dash by 2S plus J X2 dash by 2 in parallel with JXM by 2. That means these portions are remains unaltered, xm by 2, and here it is also xm by 2, only the resistance part which is related with slip, that has been changed. So similarly, the rotor impedance representing the effect of backward field referred to the stator winding M is given by R2 dash by 2 into 2 minus S plus Jx2 dash by 2 in parallel with Jxm by 2. So this is for backward field. Now in order to simplify the total calculation, we will define the following impedances in this way. That is for impedance for forward field, that is Rf plus Jxf, where we have put all the values of Rf, that is R2 dash by 2S plus Jx2 dash by 2, and it is definitely parallel with Jxm by 2. And similarly, backward field we can also calculate Rb plus Jxb, that is R2 dash by 2 into 2 minus S plus Jx2 dash by 2, which is again parallel with Jxm by 2. So here Jf is the rotor impedance referred to forward field and Jb is the rotor impedance referred to backward field. And calculating this one, we are getting the values of forward field and backward field, and putting all those values, we can again simplify the single phase induction motor equivalent circuit with only its main winding energized. We have put the values of Zf and Zb, forward field and backward field impedances, and we have simplified the circuit into a smaller one. Now from this simplified circuit, we can easily calculate the current, which is definitely a series circuit. It is Im, we can easily calculate by Vm divided by Z1M, which is the impedance for motor main winding, and then plus Zf plus Zb, backward field and forward field impedance. In that way, we can easily calculate the current of stator winding. So up to this much is for today. In my next lecture, we will learn about the performance equation calculations from equivalent circuit. Then we will do some numerical problems, and equivalent circuit of single phase induction motor is very important, and the total thing has been modified. It is similar like transformer equivalent circuit, only the difference part is on rotor side due to the forward field and backward field. And as the forward field and backward field, they are just equal and opposite in nature. So according to the slip has been already changed, and the forward field value of resistances has been modified, and equivalent induction motor also changed. So thank you for listening my lecture, and this total lecture is based on Ashfakushyan equivalent circuit of single phase induction motor. You can go through that book and definitely solve different kinds of numericals related to that. Thank you. Thank you for listening my lecture.